Okay, so we're going to take you through a case study here, a progression of an acid-base imbalance, and show you how it goes from normal to uncompensated to partially compensated to fully compensated. So what I've got here is I've got my scale down here. This is my carbonic acid. This is my bicarbonate. This is controlled by the respiratory system. This is controlled by the renal system. This is my acid side of the scale. This is my alkaline side of the scale. My scale's at 7.40, which is more basic than acidic, so I have to have more bases than I do acids. So this ratio is 1 to 20. I've got 1.2 milliequivalents of carbonic acid and 24 milliequivalents on average of bicarbonate. That maintains that range. So I have this patient that comes in, and so they woke up in the morning, and when I looked at if I were to look at their variables, everything was normal. So let's say that we were able to take their arterial blood gas, and let's say that their pH was 7.40, so that would be normal. Their PCO2 is at 40, and let's say their bicarbonate is at 24. So everything's great, but what happened is they ate something that just didn't agree with them. And so since they ate this thing that didn't agree with them, they decided to take Tums, or calcium bicarbonate or sodium bicarbonate. Well, as we talked about in the last video, if I take something like sodium bicarbonate and I put that in my stomach, what's going to happen is that's going to dissociate, and that's going to start to increase the pH. So now we're increasing the pH of the stomach, which stimulates the G cells to release gastrin. When gastrin is released, it's going to plug into receptors on the ECL cells to release histamine, and also the parietal cells themselves. But both of those, histamine and gastrin, are going to stimulate the parietal cells to start to increase the release of hydrogen because they activate the proton pumps. Well, if you remember, that hydrogen is actually derived from my CO2 and H2O. So I can break down glucose, get CO2 and H2O, but that gives me H2CO3. That gives me a hydrogen ion that my proton pump's going to kick out, and that's going to form hydrochloric acid in here to try to bring back down the pH into its normal range. But I also produce this bicarbonate, and that bicarbonate is going to be absorbed into the gastric blood. And so there's my alkaline tide. I keep taking bicarbonate over here and absorbing it into blood, and at the same time I'm absorbing this bicarbonate into blood also when these dissociate. So what I've done is I've gone over here to the alkaline side of my scale and I've added more bicarbonate. Well, as you can imagine, since I'm adding it on the metabolic side of my scale here, and that's going to take it and tip it to the alkaline side. So I'm actually starting to go into metabolic alkalosis. Now, initially, you're not going to see that, because initially what's going to happen is you're going to start to add bicarbonate, and your bicarbonate's going to go high. So let's say that we were able to take an arterial blood gas on this patient, and let's say they've added enough bicarbonate to take their pH to 7.42. Now that's still normal. That's going to move up to the normal range. However, their bicarbonate has actually gone outside that. Let's say it's gone to 28. Now at that point, their bicarbonate is out of range, but they haven't affected their acid-base state yet. If we looked at their PCO2, it still might be at 40. Okay. But let's say that they continue to take these Tums to try to fight this upset stomach, and what happens is they keep the Tums increase the pH, which activates the proton pump, which then I put more bicarbonate into the blood, and then the bicarbonate that I'm using to neutralize stomach acid keeps getting absorbed. Well, eventually what happened is that my base might go up. I might add enough on this side, and let's say it's at 32. And there's my serum bicarbonate, but that's finally enough to take my pH and pull it out of the normal range. So let's say this goes to 7.47. At this point, I've added enough to pull it outside that normal range, so now I have a diagnosis. I'm in metabolic, metabolic's added this side, and it's tipped to the alkaline side, so I'm in metabolic alkalosis. Now my PCO2, it might still be at this point in normal range, so let's say that it's gone to 43, okay? So right now, this is not compensating. So this is uncompensated metabolic alkalosis. If this variable hasn't moved out of the normal range, it's not compensating, and so this is uncompensated. But now let's say that this bicarbonate continues to get absorbed. I take this and I pull this up to 34, and my bicarbonate, and my pH is at 7.48. But now what's taking place is my breathing rate is starting to slow. Because my breathing rate is starting to slow because I need to take this scale that's been tipped this way and start adding acids on this side. So if I slow my breathing rate, instead of breathing off CO2 and H2O, because normally I breathe off this CO2 H2O and CO2, but that was actually derived from H2CO3. So if I start to hypoventilate and slow down my breathing, I'm going to start to take and I'm going to start to load on this side of the scale, and it's going to try to compensate. So let's say that I've slowed my breathing rate enough down that this has gone to 47. Okay, now look at this. The 47, I'm trying to send myself into respiratory acidosis to compensate for that metabolic alkalosis. Now this is called partial compensation. Because partial compensation, what happened is this has compensated, but it's not compensated enough to bring my pH back over into the normal range. However, as this starts to progress, the breathing rate is going to slow down even more. And as the breathing rate slows down even more, you might go to, let's say, 53. And at 53, that might be enough to pull my pH back over here. So now my pH is pulled to, let's say, 7.45. Okay, now that's in the normal range, but my bicarbonate, I've still added to that side, and so my bicarbonate, let's say, is still at 34. Okay, now here's what's taking place. I'm at fully compensated metabolic alkalosis. So because my CO2 has compensated enough for my bicarbonate, or my H2CO3 has compensated enough for my bicarbonate to bring the pH back into normal. So I haven't corrected, I've just compensated. So again, just to walk through this is normal. This one right here just shows you that my bicarbonate is going high. Okay, so I have an increase in bicarbonate, but not enough to affect my pH. But now what I've done is I've taken so much of the Tums that I keep activating this proton pump and keep reabsorbing here and absorbing here, that I've pulled my pH over. But my respiratory system hasn't compensated. This is uncompensated. So if you see the pH with a variable and the other variable in here, that's uncompensated. However, when the other variable moves this direction, now it's starting to compensate. It wants to compensate. And so this is called partially compensated. It's partial because my pH hasn't been pulled back over. But when I compensate enough going the other direction that I can pull my pH back over, then that's fully compensated. Okay, so this is fully compensated metabolic alkalosis. All right. Now, eventually, what's going to take place is my kidneys are going to start getting rid of this, and as my kidneys start getting rid of this, my breathing rate returns to normal, and then that would be corrected because everything moves back into the middle. Okay, but let's say that we were just given this information right here. So I'm given this information. Well, I don't know if this compensates for this, or if I have in respiratory acidosis and I'm compensating with metabolic alkalosis, or if I'm in metabolic alkalosis and I'm compensating with respiratory acidosis. At that point, you have to just look at the pH, because here my pH is 7.4. So 7.45 is more basic than it is acidic. And so your pH will tell you what drew you into it initially. So my pH is more basic, so that means I'm in metabolic alkalosis rather than respiratory acidosis.